This essay proposes a non-standard temporal framework, geometric time, that reframes time as an emergent structure arising from internal constraint, coherence, and directional geometry within physical systems. Rather than a universal metric or flowing dimension, time is treated as a resolution phenomenon shaped by anisotropy, folding, and recursion. We introduce radical acceptance as a theoretical lens. Temporal diversity is not considered deviation, but structural truth. Using examples from neutrino oscillations, Majorana fermions, semi-Dirac fermions, atmospheric gamma-ray phenomena, and engineered metamaterials, we demonstrate how time manifests asymmetrically and contextually. Geometric time thus offers a unified but non-universal model grounded in structural emergence. Time is traditionally treated as either a universal axis, Newtonian, a relativistic coordinate, Einsteinian, or a quantum parameter in standard quantum mechanics. These models assume, implicitly or explicitly, that time is externally applied or globally consistent. Yet many physical systems, particularly at quantum and high-energy scales, exhibit behaviors that defy this homogeneity. Temporal asymmetry, phase delay, and directional dispersion suggest that time arises from within systems, not from without. This essay develops geometric time as a framework of radical acceptance, a structural approach that recognizes time as the resolution of internal constraint. Temporal coherence, under this view, is not globally imposed, but locally emergent. Constraint here refers not to limitation, but to generative structure. It is the internal geometry, tension, or recursion that gives rise to coherence and transformation. From this perspective, constraint generates temporal resolution. Rather than imposing synchrony or universality, we propose accepting anisotropy, nonlinearity, and folding as valid temporal behaviors. Radical acceptance means recognizing that not all systems experience time equally, and that such differences are structurally meaningful. Neutrinos evolve through phase interference between non-degenerate mass eigenstates. This evolution is observable as a periodic oscillation between flavor states, structured by internal phase, not by an external timekeeper. Majorana fermions exhibit 720-degree phase invariance and are their own antiparticles. Their worldlines can be modeled as Mobius loops, folded topologies that preserve identity through phase symmetry rather than directional time. In systems like black phosphorus, semi-Dirac fermions show conic dispersion in one axis and parabolic dispersion in another. This leads to directional variation in phase velocity, implying structurally variant temporal resolution. Gamma-ray glows and terrestrial gamma-ray flashes, or TGFs, are Earth-based examples of high-energy, time-sensitive coherence. Structured electric fields drive field-based coherence over nonlinear durations, showcasing time asymmetry at the mesoscale. Media with temporally modulated internal structures have been shown to reverse signal propagation, creating engineered time inversion. These materials provide a testable case of structure-determined temporal behavior. Across these examples, time is not imposed but resolved. It is the structural outcome of coherence, constraint, and curvature. From quantum systems to engineered fields, time manifests as a localized capacity to transform, not a background against which transformation occurs. Geometric time opens new avenues for reinterpreting time dilation entropy and quantum measurement as emergent, not imposed phenomena. It invites models where time is a derivative of field structure, potentially bridging relativistic and quantum domains without requiring unification. Future work will formalize constraint recursion metrics and explore observational frameworks for detecting structural time signatures. Geometric time challenges the primacy of universal temporal flow. Instead, it recognizes time as the emergent product of system-specific structure. Through radical acceptance, we affirm that temporal asymmetry, anisotropy, and nonlinearity are not anomalies. They are the marks of structurally real time.